The purpose of this lesson is to explore some of the practical aspects of data mining using classification trees in KNIME. So the first thing we're going to look at is this idea of using a continuous response variable, which is what we've used in the past for linear regression, but as its name suggests, classification tree building is for classes, for predicting the classes of the response variable. So that response variable has to be categorical. Second, we're going to look at the tricky business of picking which explanatory variables, which columns to include in the model. Third, and this is a related idea, is selecting columns with the appropriate granularity. There's such a thing as being too specific and having trees that are too bushy. And finally, we're going to talk about refining the model using the testing procedures. The classification task we're going to use for this demo is predicting, or at least better understanding, the factors that contribute to the amount of a professional hockey player's salary. So is salary determined by attributes of the player, like that individual's size and the position they play, or is it simply a function of their performance on the ice in terms of goals, assists, and so on? Or is it more situational? Is it due to, say, their nationality or the size of the market that their team is in? So what we want to do is take a data set that contains hockey player salaries plus all these situational player and performance data points and try to see if we can learn any interesting relationships. The first thing we're going to look at in KNIME is this idea of binning a continuous response variable, which means transforming it or recoding it into a categorical response variable. So we start with our data on hockey players, and the response variable salary is obviously continuous valued. So what we can do is we can take a look at this data with a histogram and hopefully identify some fairly distinct categories or classes of salaries. So example, we can see sort of the low end of the scale, players making a medium amount, and then of course the stars, the players making the highest salaries. So that's the first task that we're going to set for ourselves in KNIME. What I have here in KNIME is just a file reader, and hopefully you can see that I've just opened a comma-separated variable file containing the hockey data. Now, KNIME, being open source, doesn't seem to play very well with Microsoft Excel, which is pretty typical. So we use comma-separated values, and if I scroll through my data, I can see that I have a whole bunch of performance and player attributes, and I have my total annual salary, and I've expressed this in millions to make it a little bit easier to work with later on. So if I get rid of that, the next thing I want to do, of course, is look at this data. So what I go to views, and I can use my interactive histogram, make sure that that's run, and it is. So I've got a green light there, and then I can connect them up. So amber light now, I have to configure this and get rid of that. What I really want to do is get a histogram of the total annual pay in millions of dollars. So I click on that and hit OK. And then now when I run and look at this, I get a fairly standard histogram. Now notice here I have a nice feature. I can go to bin settings and I can change the number of bins. So I can sort of, we talked earlier about how many bins should I use in a histogram. Well, this tool actually gives you some sense of what different kind of bins look like. So what you would normally do then is you'd have some sense of what these natural categories are of salaries within the business context. What are low paid players paid? What are medium players paid? And what are the stars paid? And if you want, you can click on any one of these bins and hit details, and you can't really see it, so I'll drag it up. You get actually the value. So this bin corresponds to 4.8 to $5.05 million. So you have all your bins, and hopefully you can use those thresholds to create categories. Okay, so the next thing I can do is get rid of my histogram and actually use the binner. Now in KNIME, you can navigate these features, or you can just sort of type in what you want, and that's what I've started to do. And I see here what's called the numeric binner. So I can drop a numeric binner on this and connect it. Try again, connect it, and then configure it. And the first thing that I have to say is which column do I want to bin. So I hit total annual pay, and I'm going to have three categories. So I go add, 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 and it creates bin 1, 2, and 3. Those aren't very useful names, so I'm going to rename them low salary, medium salary, and high salary for the players. Then, if I go back to low, I can specify the interval. So low here is negative infinity. That's what this box here says, to some value. Now, when I was looking at my histogram, I decided $1.9 million was going to be the threshold for low salaries. And now medium is going to go from 1.9, which is picked up automatically, to I went 4.6. Okay, and that means high is then going to be 4.6 to infinity. So I go down here and I want to also check append a new column. So this is going to create a new column called annual pay, and you see with a binned suffix on it. So I hit OK, and I can run that, and of course it doesn't do anything. It just goes off and does the transformation. So if I want to see actually what happened, I can type in pi, and there's a couple different pie charts. I'll just drop on a simple pie chart, connect it up, and configure it. And what I want to do then is see the distribution of this new binned column. Get rid of the aggregation column, don't need that. Hit OK, and then when I run this, I should get a distribution. So what you see here is a bit lumpy. It's a little bit uneven. First of all, 51%, almost 52% of my players fall into the low category. The medium category is about a third of my players, and my high category is only about 11% of my players, which may make sense in a business in business terms, but we're going to see that actually creates some problems when you're data mining, especially at the high end, because I don't really have enough data. Or put it differently, I know right now that almost 52% of my players are going to be in the low category. That's my a priori estimate of the probability of being low. So my prediction's almost always going to be low. Really what I want to do is to be able to predict all these different classes of salary. So another approach is, instead of having business-oriented bins, is to create just thirds, top third, bottom third, equal size bins. So I don't want pie charts, sorry, I want binner. And there's this thing called an auto binner. So I can drag this in, just find a spot for it, maybe not there, and connect it up means the data now goes from the file reader to all these different nodes. But the auto binner, oops, click on it, right click, the auto binner allows me to automatically bin. So first of all, the first thing it does is it bins everything, which isn't what I want. So I hit remove all, and I scroll down and I say I only want to bin total pay, and I can just add that. And let's say what I want is top third, middle third, bottom third. So that's 3 bins, and I want them to be equal frequency, not equal width in terms of dollars, but equal frequency in terms of number of players. I want the bottom third of my players, the middle third of my players, and the top third of my players. There's a couple other things here to set. How do you want to name these automatically generated bins? Well, I'm going to use the borders. the high and the low points, because that makes the most sense. So you can't see it, but I'm just going to hit OK. I can run that. Nothing happens, of course, but I can drop a pie chart onto it to see my thirds. So I just connect it up and configure it. And I go through this again. I only want to see my new column. I don't want an aggregation column. That should be good. Right click, execute and open views. And I get exactly what I think I should have. I get a pie chart with 3 equal segments. So my lowest category here looks to be between my lowest salary, sort of $300,000, and 1.24 million. Then my next category is 1.24 million up to 2.4 million, and my highest salary group is 2.4 million to 9.5 million. So these categories are quite different, but remember the idea here is to have what's called a balanced set of classes, balanced in the sense that they're all the same size. Now the nice thing about this is, from terms of my prior predictions, every player is, if I take any player, that player is equally likely to fall into any one of these 3 categories: high, medium, or low. And you'll see that that gives us sort of the greatest lift, or the greatest information advantage from our model. The next thing we want to do in our model is to determine which columns or which explanatory variables to include in the model. And the easiest way to sort of get a sense for this is to make some mistakes. So what I'm going to do is I'm going to jump right into adding a decision tree learner to this model. So I drop in a decision tree learner, and I'm going to connect it to my auto binned values. So I'm going to use my balanced categories, my top third, middle third, bottom third. And to configure this, select one only, configure it. I'm just going to accept the defaults. It's somehow figured out that the classification, or the response variable, is total annual pay that's been binned, and I'll accept all the defaults here for the learning. And remember what we've got. I brought in some data. I used AutoBinner to recode my various measures of salary into high, medium, and low salaries. And then I'm going to use a classification tree to predict which class a particular player falls into: high salary, medium salary, low salary. And let's see how this works. So what happens is I get a tree that basically says the best predictor of the salary category is the actual salary. Okay, so the first thing it says is if a player makes less than $1.24 million, then there's a 100% probability that that player is going to be in the lowest category. Remember, I just used these intervals for the name of the category. So 100%, 304 players that make less than $1.24 million fall into the less than $1.42 million category. Newsflash. The issue here is that I've done nothing of business value, but I've at least convinced myself that the decision tree works, or the classification tree works, because it's actually discovered my bins. So for example, 100% of the players making more than $2.4 million are in the more than $2.4 million categories. The algorithm sort of discovered these thresholds by itself, and fortunately it discovered the right thresholds. Now another point here, you could see that these are binary splits. So the first split is on total annual pay, and there's 2 types of players: players making less than 1.24 million and players making more than 1.24 million. And in the block where they make more than 1.24 million, the results are kind of split 50-50 in terms of being in the highest class and the middle class. But then it splits again on the exact same variable. It splits again on total annual pay, and here's where we get this perfect discrimination. 100% of the medium players are in the medium category, and of course 100% of the highest paid players making more than 2.41 million are in the more than 2.41 million category. So it should be obvious here that including total annual pay to predict total annual pay binned is completely silly. So what we have to do then is add some ability to filter out certain columns, because you'll see certain columns just don't make sense. So I picked the filter and I'm going to drop it actually onto that line, and KNIME does a pretty good job of making room for it, although at this resolution I have to move some stuff around. Now column filter is pretty straightforward. We've seen something like this. By definition, or by default, it gives you all your columns. So what I want to do is go through and take out basically the other response variables. Total annual pay, the binned version, is my response variable. I certainly don't want total annual pay as a predictor variable or as an explanatory variable. Clearly, it's related in a trivial way. And here's also total annual pay, which was in dollars, not millions of dollars. And you just scroll through and make sure you have no other variables that are obviously irrelevant or obviously not going to have a useful predictive role. So I leave it like that, and I can then just run it again. I can go to the final node and run it, and it will make the adjustments. So now I'm getting something that, at least on the surface, looks a little bit more useful. It says, you know, there's two types of players. There's players who have less than 10.5 assists per unit of time, and those who have more. To understand the issue of granularity, let's drill down a little bit more on our decision tree here. So we split on the sum of assists, and then if we go down a level, all of a sudden we see sort of chaos. And if we look over here at the top right, at the miniature thumbnail version of the tree, we see that it's all of a sudden extremely bushy or extremely wide. And what the reason for that is that the next variable to split on under assists is the name of the player's team. And you can see why maybe this would be a good splitter is in certain situations here, let me try to find one, we have situations with perfect discrimination. That is, for players who have lots of assists and they happen to play for Anaheim, the 100% of those players were in the high pay category. But there's only 2 data points here. So there's a whole bunch of problems with this bushiness. First is you're cutting your data into extremely small bins, and you're going to run out of data. You really don't have the amount of data to split on something like team where there's 32 or 35 different variables sort of historically, or 32, 35 values historically. The second thing is that this has almost no business meaning. Do I really believe that, you know, Tampa Bay and Florida and Nashville have completely different pay structures in a competitive environment? So what I'm going to do is I'm going to say, you know what, team is not a good measure. It's too granular, it's too specific, and as a side effect of the way the algorithm works, where it's looking for these perfect splits, it gets suckered into creating a split that has no business value. So I'm going to go back to my column filter and hit configure and start to take out columns that I think are too specific. So player ID, for example, is the obvious choice. There's one player ID per player. You know, if I know the player's ID, I 100% know that player's salary, but that's not generalizable. I can't, as an agent or as a team, say, oh, you know, players with this ID should earn this much. You know, what we really want to do as an agent or as a general manager is say, you know, players with these characteristics and this kind of performance should be making this kind of money. That would be useful. So I get rid of player ID. Height and weight, you know, the integer ones or the numerical ones are good because they're not categorical. They won't result in bushy splits, as we've seen with assists. KNIME splits numerical or continuous value variables in half. It finds a good split point, so bushiness isn't a problem. Here I have position, which is right wing, left wing, and so on. I'm going to get rid of it because to me, position general is a better variable. Are they forwards? Are they defense? There's no goalies in this data set. I don't need birth date. I mean, I can't imagine that that's relevant. Birth year might be relevant. Country, do I really believe that Latvians are paid differently from Belarusians? Probably not. Although North Americans, Europeans, Asians, and others may be paid differently in the league. So I'm going to leave region in, but take country out. Region is coarser grained and to me more useful. Drafted by is the name of a team. I mean, I know when I have 30 teams, I run into bushiness problems. Draft number, draft year. The rest of these actually look okay. Season ID is a measure of time. Which team they're on, I don't care. So I'll get rid of team. But I do want to keep market size. So some teams are in large markets, like New York. Other teams are in very small markets, like Tampa. And the rest of these are numerical, so these are all performance measures, shots, power play goals, and so on. And there's my response variable. So I've cleaned this up a little bit, and now I can rerun this, and I should get a more useful classification tree, more useful from a business point of view, more useful in being able to predict. And we see as we click through this that it really comes down to offense. I mean, you could spend hours going through this, but basically assists and shots on net seem to be what's driving the big money in professional hockey. Now, remember when I created my tree, there were some parameters that I could set, and I just sort of ignored these and said, well, I'll pick those later. I want to get the basic model in place. Well, now's a good time to think about, well, refining the model and making the right choices. But it's kind of hard right now because I'm in a vacuum. I don't have any sense of whether my model's good or bad. So remember, what we can do is set up sort of a testing regime or a testing sort of platform by taking our data and partitioning it into a training set and a testing set. So I link up a partitioning node, and what a partitioning node does is allows me to split my data into two. So 60% of my data is going to go to the top branch, and 40% is going to go to the bottom branch. So what I can do is I can just Control copy, Control V, this decision tree, and that's going to be my learner. It's going to use 60% of my data, and I'm going to bring in a decision tree predictor, which uses this model to predict the outcomes of a different set. So I have to link these up square to square here. Oops, takes a little bit of practice. And recall my data comes in from the bottom part of my partitioner. So this is fresh data. This is 40% of my data set. These are hockey players who I know what they made. I know what their salary is. There's a value there, but I also know their characteristics. So what this is going to do, this predictor, is it's going to say, well, given their characteristics, what do I predict their salary is going to be, and what is their actual salary? And then I can use a scorer to sort of keep track of right versus wrong. And this gives me the infrastructure to tweak my model and see, do I get better accuracy with this configuration or that configuration? I do have to configure the scorer just sort of trivially. Click on configure and say yes, compare the predicted value of bind, or sorry, the actual value of bind to the predicted value, and count hits and misses. So I can go off and I can execute and open this view, and I get what's called the confusion matrix, which basically says in the column it's what was the player's actual salary bin, the lowest one, the medium one, or the high one, and then along the top it's what was predicted. Okay, so there's the low one, the medium, and the high one. And really what we're interested in is these diagonals, because those are correctly classified cases. You know, uh, was actually low and predicted low. The player was actually in the medium bin and it was predicted to be in the medium bin, or the player was in the highest bin and was predicted as such. So what this tells me is that my accuracy is only about 52%. Which isn't bad because I started off with balanced categories, top third, middle third, bottom third. So if I didn't know anything about a player, and I predicted the player would be in, say, the low or the medium or the high category, I'd be right 33% of the time. Using this model, I'm going to be right 52% of the time, at least on average. But I want to see if I can increase um, my accuracy. So one of the first things you should probably do is use pruning. What pruning does is prevent overlearning, which is a bit of a technical topic, but it keeps the tree from going too low and getting to very, very small data sets and making predictions based on 5 or 6 observations. So I'll just turn on the one pruning option and I hit OK. And then when I run this, we can see if it has any change on my prediction accuracy. And there now my accuracy is up, a little bit closer to 57, 58%. So that's a pretty big gain. And you can see that, I'm still wrong quite a bit, but it's slightly better. Now I should say as well, the confusion matrix is one way to look at your accuracy. If you click on the scorer, there's also a set of accuracy statistics. Now this is a little bit more involved, but at the same time, it's more useful because, we're not so much interested, if I was a player or an agent or a general manager, I'm really interested in sort of certain categories, like for example, the high salary or the top third of players. I want to be maybe much better at predicting, the top tier salaries than the mid and the bottom tiers. So you get things like, number of true positives, 50 times I said players would be in the top tier and they weren't. 189 times I said they weren't in the top tier, and in fact, I was correct. So there's these true positives, false positives, and so on. And then there's some ratios, things like sensitivity. How well can I spot high value players or high salary players? So I'm not going to say much about that, except that I think at an intuitive level, you see that the performance of this model can vary depending on whether you're looking at the lowest category or the highest category, highest salary players. So what I do is once I get my model sort of where I want in terms of both business meaning and accuracy, I sort of take a note, if you like, of what these parameters are, and beg your pardon, and I go over here and copy them to my all data case. And I'm actually going to relabel this all data. I can double click on it, call all data. And really what this is my best model that's using all the data. So here my testing stream allows me to predict how to configure this tree, but once I get it configured, it makes some sense to go back and use the all data node so that when I execute and run this, I get the best possible prediction using, in this case, all 913 pieces of data rather than using just a subset is what I get when I partition the data during testing.